Let me check your average. I think the average is quite high. Yeah, the average is 68. 68. I will deliver the results maybe 220, okay, around 220. Or maybe 230, yeah, around that time. So we'll start okay, so let me continue a little bit. It's still the trigonometry and integrals. Okay. So basically, this identity is important in this integration. Let me just give you the example and see the solutions. Okay. So if you have now, I will going through the tangent form. The tangent. If you have tangent 5x and then secant 7x there. So in trigonometric integrals, we are combining the identity in trigonometry and also the use substitution. And also this is because you are going to use the substitutions. The derivative of secant x and derivative of tangent x become important. So the derivative of secant x become the secant x tangent x, and derivative of tangent x becomes secant squared x. Okay. Now, if we see this tangent 5 and secant 7, the idea is similar what we did in Tuesday. We can split, we can separate, okay? And we can separate and make becoming this secant tangent or secant squared, okay? But you see that we have odd 5, 7. So I think if we can make tangent and secant separate, and the other one become the even, right? So let's just try and write this as tangent 4, and then it becomes secant 6. And then the other part is secant x, tangent x, dx. Okay. Now this even, you have the even tangent 4 and secant 6. Tangent 4 and secant 6, we can compute and interchange tangent square or secant square with the identity. Either tangent squared becomes secant squared or secant squared becomes tangent squared. Okay. Okay, now because we have secant x tangent x, so the secant x tangent x is obvious. This expression is to be cancelled. It's to be cancelled. So we need to imagine the functions before we derive. The derivative in which resulting secant x tangent x is the secant x, right? So we need to sub the secant x. So we need to change the tangent into secant, okay? So this become secant squared x minus 1 and then squared, okay? That become the tangent squared and then squared, it become 4, right? And then the other one, let me write the rest. Okay. And the rest is substitution. Okay. We need to sub the secant x. Okay. So let the secant x is, or maybe u is secant x, and then du is secant x tangent x dx. So we can cancel the secant x tangent x. So we get the whole integrations become u squared minus u and then squared and then u6, okay? And then the rest is only du, okay? We can directly maybe open the quadratic. This become 4 and plus 1 and then u6, okay? And then we integrate um, or let me write down all the informations here. Okay? So integrate, and I will write directly the answers. So u is the secant x, so secant 11x minus 2 over 9 secant 9x plus 1 over 7 secant 7x plus c. Okay. 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 Don't forget that you can actually plus c here, but to avoid any confusion, just plus c at the very end. Okay. Okay. This is where if we want to use the substitutions is the secant x. Okay. So if we have um, this odd 5, 7, okay. So we split tangent, split secant, and it becomes even, right? The number here. If it's even, then we can exchange to secant and tangent squared. Okay. So we split, and then it's become 4, 6, and we can um, exchange one of this. And because this is the secant x tangent x, we need to sub the secant. So we need to change all to secant form. Okay, okay, that's the idea for tangent. Okay. Another possible questions if you have the all even. So for example, tangent 6, secant 4. Now, the idea behind the secant and tangent, the left side is odd, 5, 7 is even, 6, 4. If you have odd, you have secant x tangent x. You separate, and this become 4, 6. Okay. So the idea is to keep the whole number here is even. So if you have 6, 4 is the even number. Okay. So if you have this, the idea is still the same. So you need to keep the big part here even. So you need to separate secant squared. Now secant squared, not the secant tangent. Okay. So let me write for you. Okay, let me write for you. Okay. Now, if we compare, I hope you can see the comparison. The idea is still you need to have even here, and this is also even. Okay. Get the idea? Get the idea? This is odd. This is even. But when you separate, you need to keep the whole bigger number here. The one in the left here. That should be tangent and secant should be in even. Okay. So 6, 2. This is 4, 6. Okay. So that's the idea. And what we need to sub for the left part is secant x tangent x, right? So you need to remember what is the functions before the secant x tangent x, before you derive. Okay? Before derive, it's secant x, right? So you need to sub or you need to change secant x. That's why all the form on the left, you need to write in secant form. Okay? So tangent, you need to write in secant. And this also similar, but now you have secant squared here. Secant squared before secant squared is tangent, right? So you need to change all into tangent to sub. Okay, got it? Okay. So why the left part should be even is because the tangent squared plus 1 is secant squared. That's the relation. So that's why you need to keep the left part even. Okay. Okay, got the idea? Okay. Okay, let me continue here. So this part, I will change this to and then make it the u is the tangent x now. And du will be the secant squared x dx. So we can cancel the secant squared. So we will have u6 and then u squared plus 1. I think just that. So we will have, let me write 8 plus u6. And we can integrate this, become 1 over 9. Now it's tangent 9x plus 1 over 7, tangent 7x, and then plus c. Do you need to write the official definitions? Like if the tangent is odd, if secant is odd or even. But let me write the official definitions for you. It'll be right here. So tangent mx secant nx dx. So if secant is even, meaning the n, okay, so 2k. So tangent mx secant 2k x, or let me write directly. Let me write in secant squared and then k minus 1. And then secant squared x. Yeah, this is what we did actually, what we did. And then we can change this into tangent. And then we can write that the u is tangent x. We can substitute the tangent x. And for b, if tangent is odd. So tangent 2k plus 1x, and it's secant and x dx. Let me write below. This become tangent squared x to k, and then the other one will be secant x n minus 1, and then the other part is secant x and tangent x. So from here that you can make conclusion that this substitution should be the secant x. And this should be secant squared x minus 1. Okay. So basically, when you solve variations in secant tangent with power, you can actually trial and error. You can try split the secant x tangent x or split the secant squared x. Only two possibilities if you want to try. If you cannot solve it, then you need to try another method. Maybe most of the cases you can do with the integration by parts. Okay, so I think for trigonometric integrals, we only have the sine, cosine, and secant tangent, okay? And exchange the relations between the identity, okay? And then use the substitutions method. Now the next section after this is the we call the trigonometric substitution. Okay. It's different. It's different. Okay. So it's called the trigonometric substitutions. Let me just write sub. Okay. Meaning the substitutions is we need to sub the variables with trigonometric functions. And again, we are dealing with the basic identity in trigonometry, the sine squared x plus cos squared x equal 1, tangent squared x plus 1 equals secant squared x. Okay. We are using the same particular identity most of the cases. Okay. Okay, I will give you like 3 examples, and then we can make conclusions, okay, from the examples. Now we have integrations 1 over x squared and then square root of x squared minus 9. Okay. Okay, so the idea for the trig sub, we need to substitute the x, okay? Substitute the x, the variables, with trigonometric functions. Okay, you will see we have the x squared minus something. Okay, if you see from our identity, sine squared plus cos squared 1, and then tangent squared plus 1 is secant squared. We have now, in particular, in below the square root, we have x squared minus something, minus the constant. So we need to substitute x squared with trigonometric functions, and then we need to simplify the form in another variables. Okay. So for example, if you have x squared minus 9, based on our two examples here for identity, sine plus cos. If you want to make it x squared minus constant, I think you cannot, right? You only have sine squared is 1 minus cos or 1 minus sine, right? But in tangent, you will directly get, if you move 1 to the right side, you get tangent squared is secant squared minus 1, right? Variables minus constant. Exactly what we are dealing here. So the idea is we need to substitute the x with secant. But it's not only secant, we have constant 9. So we need to substitute with 3 secant. So when we square, it becomes 9 secant squared. Okay, so let me write these substitutions. So let the x is 3, or let me use bright color. X is 3 secant. Let me use theta. Okay. And we have also the x is 3 secant tangent theta d theta. Okay, so we need to substitute x and dx. So we substitute the x. Let me write this 3 secant theta tangent theta and then d theta. And then this becomes 9 secant squared theta. Let me write the whole expression. 9. I will, let me write here. X squared is 9 secant squared theta. Okay. So this becomes secant squared theta minus 1. Okay. Now the secant squared minus 1 is tangent squared, right? This tangent squared. So 9 tangent squared theta. We square the 9 tangent squared becomes 3 tangent. Okay, 3 tangent. So this becomes 3, or let me just remove the secant and remove the 3. So tangent theta, d theta, secant theta, and then it's 3, and then another 3, tangent theta. So it becomes 1 over 9. Let me cancel tangent. And then 1 over secant theta becomes cos theta d theta. And this is 1 over 9 sine theta plus. If you want to, it depends on the conditions, but usually we need to turn back to original equations. Like we have theta here, but the question is in x, so we need to change theta to x. So how to do that? We can use the triangle. So the secant theta, secant theta is x over 3. So cos theta is 3 over x. So let me draw the theta here, and then 3x. And this becomes x squared minus 9. So sine theta becomes and plus. Okay. So you need to revert back to the x. Okay. From here. So we are already left the x is equal 3 secant theta, right? So we can use that definitions in our triangle, and then we look for the sine, right? Because our answer is sine theta. So sine theta is this, right? Oh, here, x. Sorry. Okay. Okay, that's the first example. Let me write here. This is the first one. The second one. Second one is integrations x cubed 9 minus x squared dx. Now we have the inside the square root, we have a constant minus x squared. Okay. So usually trig substitutions, basically the basic one is substituting the squared one, but depends on the questions. Maybe they will combine with other functions. But usually uh, the basic one is just substituting the squared part of the variables. Okay. Now we have constant minus variables. Okay. So based on our identity, we can substitute 1 minus cos or 1 minus sine. Okay. So you can choose between cos and sine. So we can choose this, become let the x is equal. Let me just use sine, okay? Because when I derive, it's positive. And then we need to change all with the 3 sine theta. become 1 minus sine squared. And then the dx is 3 cos theta d theta. The whole thing become 9 cos squared theta. This becomes 3 cos theta. Okay. So I will group all three. Okay. So we have 3, 3, and then 3 with power of 3. So it becomes 3 to the 5. So we have 5, 3. So I will group that and remove from the integration. So I will put here. And then we have sine cube, and then it's cos squared. Now we still need to solve this whole equations. We can use these just regular substitutions. Okay. Whenever you this is just a suggestion. Sometimes when you are dealing with integration and you need to use more than 2 or 3 substitutions, okay? My suggestion is always change the variables, okay? Always change the variables. Maybe now u, and then maybe the next one, if you still find it, you need to substitute. Maybe you need to change to v or z, y, okay? If you use the same u, maybe you will be confused, okay, when you're calculating. Okay, so always change variables when you're. So if you have functions inside functions that you need to substitute with different variables, okay, to help you distinguish which one you are really looking for. Okay. So now, because I now have theta from x, I will use u for substitution. So let u is say cos theta. Why I'm using the u? Because I can have this 1 minus cos squared, and then I still have sine theta, in which I can cancel. Okay? It's like the trigonometric integrals, like last Tuesday. So I will substitute cos theta as u. Okay. Now I will get the 1 minus u squared, and then we still have u squared, and then become minus. And the constant is still the same, 3 to the 5. And then the now we can solve this. So this becomes u squared minus u4. I will put the negative inside. So it's become 1 over 5. U is cos theta. Cos 5 theta. And then minus 1 over 3 cos power 3 theta. Okay, let me solve this first. Cos theta. Again, we can use the triangle. Look for the triangle. So sine theta is x over 3. So x and 3. So this becomes 9 minus x squared. So cos theta is, right, okay. Now, this becomes, let me just write 9 minus x squared, 3, 5. Oh, wait. It should be still 3, and then, wait, wrong. Okay, I think that's good. And this is cube. Okay, quite long. And then, oh, this is actually can cancel this. And 3, 3. So this becomes 3, 2. 3, 4, 6 becomes 3, so it cancels. So it should be 1 over 5. What is should be 5 over 2. And it should be minus 3. 9 over x squared. It should be 3 over 2. And then plus c. So this is the answer. Okay. So let me explain to you. Okay, I think the idea for trig sub is until here, okay? So trig sub is just simplifying this square root, okay? So you get the second form here, okay? So the trig sub purpose is just making this form, in which this form can be solved through the regular substitutions, okay? The trigonometric integral substitutions. Okay? So we are just using cosine and change the form, and then solve, and we get a little bit complicated, but actually it's not too complicated. Cos to the 5, cos 3, and because it's still in cosine theta, we need to get to original equation, the x. So we need to define cos theta in terms of x. Okay? And that's why I need to change the cos theta into this square of 9 minus x squared over 3, etc., etc. And notice that from the first example, the second example, I'm using the triangle, right? So meaning the total angle should be the same as this triangle. So it will have certain angle because you have the square root, right? You cannot have negative here, right? Yeah. That should be defined in its domain. Okay? It should be defined in its domain. Okay? Okay, so this is the second example. Okay. We have only 3 examples. Okay, so 1, 2, and then the third one. And I will give you a conclusion after finish all of this. Okay. So the third one is you have plus, you have x squared plus constant. Okay. So before is constant minus the x squared. Now x squared plus a constant. Now the most obvious one is if you see this identity. Okay. So of course, the easiest substitution that we can assume for x, if we are using the tangent. Okay. So let change the x. So let x is equal 3 tangent theta, and dx will be 3 secant squared theta d theta. So this becomes tangent squared theta plus 1, 9. And this becomes 3 secant squared theta d theta. This becomes 9 secant squared theta. So we can write the 3 tangent cube, and then 3 secant theta, and then 3 secant squared theta d theta. So this is cancel, cancel, and cancel. And let me remove the constant to outside. So we have tangent cube theta and secant theta. And based on what we did before in the first half of the lecture, I will separate this secant tangent. So I will have tangent squared theta and secant theta tangent theta. And I will make the tangent squared become secant squared. Oh, too small. Okay. So after we are substitute the x with the tangent, we get the lower part become 9 secant squared, and then square root become 3 secant theta, and we can cancel this with the other form, and our form becomes tangent cube and secant theta. Okay. Remember the first half of the course before? So this is odd functions, right? Let's make it even. Okay. So we have tangent squared, and then it's become secant and tangent. Because secant tangent is before is secant. So we need to substitute secant, and we need to change the tangent into secant. Okay. So we need to substitute the secant. Okay. So let the u is secant theta, and the derivative is secant theta tangent theta d theta. So we'll still write 27. We can write this as u squared minus 1 d. Okay. And this becomes 1 over 3 secant, and minus the secant theta. And as you know, we need to revert to the x. Let me go back to here. So tangent theta is x over 3. Okay. So x and 3. So we have here is 9 plus x squared. So let me write cos theta is 3 over 9 plus x squared. So our secant become 9 plus x squared over 3. Okay. And we need to substitute back the secant theta into our equation. Okay. So substitute back here. So 27, 1 over 3, and then so 1 over 3, three over 2 minus 1 over 9 square root plus c. Okay, so that's all three examples. Yeah, three examples. I will write conclusions for all the trigonometric sum. Okay, so there's only three possibility for substitution for the trig sum. Okay. So we did the secant, we did the tangent, we did the sine or cos. That's a three possibility. So you have a pattern. You have x squared minus constant. You have some constant minus x squared, and you have x squared plus. And this should be secant. This should be sine or cosine. And this should be tangent. Okay, only three possibilities. Okay? Whenever you see the form. Okay? Should be inside the square root. Or let me write the whole thing. Okay? The official one. So if you have a squared minus x squared, so this should be x is a sine. Let's just write a sine theta. Okay? You can write also cosine. And the theta should be from this interval. This is start from 0. Or okay, all the domain is to make sure that the results is positive. Okay. Okay, any questions? Okay. So I think that's all for the trigonometric substitutions. I will give you some practice but later. Okay, so I will give you all the methods from integration by parts, the trigonometric integrals, trigonometric substitutions, and the last one is partial fractions. But I think I will just go for some introductions, okay, for partial fractions. I think next week we can still review and giving you some practice from all the methods. Okay, so I'm giving you the concept for the methods and later giving you the practice. So partial fractions. Okay, so let's cause let me write some fractions, fractional functions. 2 over x minus 1, x plus 2. And let me complete this, become x squared plus x minus 2. And this become 2x plus 2 and minus x minus 1. Okay. And I can simplify this to x plus 5, and then x squared plus x minus 2. So the idea of partial fractions, if you have the integration of x plus 5 and then x squared plus x minus 2 dx. Okay. Because I already giving you the information that the x plus 5 over x squared plus x minus 2 is from these two separate functions, right? Two separate 2 over x minus 1, 1 over x plus 2. I can separate this, become 2, and then integrate each function. Okay. So this become integrations 2 over x minus 1 dx. And the other one is 1 x plus 2 dx. Okay. This become 2 ln x minus 1 minus ln x plus 2 and then plus c. Okay. That's the first idea that I want to show you. So if you're having integrations and then you have a big fractions like this one, the first idea is, can you separate this into several functions? If you can separate them, it is easier to calculate, right? Rather than you are looking for substitutions like u equal, and then you can find like the quiz, the last questions. Okay, actually you can separate them and then you can evaluate each one, and it's easier to evaluate if you separate. So the idea is, if you have the functions, it's rational functions. The px is the polynomial. Let me write the general definition of polynomial. If p, this means the degree, the power on p, the power on polynomial. If the degree is n, and p is greater than q degree, you can use long division. So your fx, let me write the px over qx. It's become the s plus the remainder. Okay. So you can use long division in polynomial and rewrite the rational functions to become the separate functions. Okay. So this happens if p, the degree on p, the polynomial p is greater than q, okay, or the same, equal or greater. Okay. Like for example, you have x cubed plus x divided by x minus 1 dx. Okay, I think this one, because the bottom one is only x minus 1, it's only linear. You can divide by the the polynomial long division or syntactic division. So you can divide this, or using the syntactic divisions. So 1, 0, 1, 0. Divide by x minus 1 is x equal 1. If you put x equal 1 into functions, if it is roots, it becomes 0, right? But I believe it's not. It should be the remainder, not 0. So this 2, 2, 2. Okay. So you have 1, 1, 2, 2 here. So this is let me write here. So this become x squared plus x plus 2, and then plus 2 over x minus 1. Okay. And then you can integrate each one. Okay, integrate. Okay, got the idea? Okay. So if you have the degrees greater than the bottom one, you can divide them using long division, and you can integrate each one easily. Okay. Instead, like looking at this form, whenever any method that you can think of, for example, you think maybe substitution. I think substitution maybe substitute x minus 1. No use, right? Substitute x cubed plus x. Also, if you derive, it becomes 3x squared, and you'll getting lost, right? If you're using the integration by parts, also what is u, what is dv, right? You need to separate which one is u, which one is dv. It's also not sure which one, right? But when you are doing the long division and separate all become these functions, it's much more easier, But don't forget, maybe in each terms here, maybe like the last one here, maybe it's still having some complex here, and maybe you need to substitutions, or maybe trigonometric. It depends on the functions. Okay? But usually, if you just use long division, the first part here is become really easy function. But still, here sometimes you need to use the substitutions, substitutions method. Okay? But I think here is just ln, right? Okay, I will continue just a little bit more, and then I can give you your quiz results. Okay. Okay, a little bit more. So if the functions, okay, let me write the p over q. If q is factorable, you can factorize. If this is factorable, then factor it. The first one, and then the second one, we need to express a proper rational function for the remainder. It can be expressed as sum of partial fractions. Like this form, or Okay, so whenever you find, okay, if you doing the partial fractions, if you find in the bottom it's only linear functions, and then maybe square and then cube, or maybe just one, the top one should be in the a constant, should be a constant. But when you have the bottom one is the quadratic functions, the top one should be in ax plus b. Okay? So this is really important. So if you have bx over qx, okay, so this should be, you have a, for example, this is just my example, okay, so maybe this is ax plus b, and then plus b same, and then squared, and then maybe cx plus d, and then this is ax squared plus bx plus c. But maybe it's different a. Okay, maybe e. This is just examples. Okay. So we need to express the rational functions as the left form here, or like this one. If you have the left form here, you will get at least it will become the ln, right? Because it's constant. And for the right side, maybe you can use the sub, u sub. Okay? You can use u sub. Okay. Let me give you a few minutes. The case one, if the qx is product of linear factors. Linear factors, if you have like x plus b, and then you have another x plus b squared, okay? Let me write first the qx. Let's say k. So Rx over Qx this if no factor repeated. Okay. So A1, A2, B1, B2, it's different constant. Okay. So you need to separate this, become each constant and each A1, B1, A2, B2. Okay. I will give you the example, and then we can stop until this first case. Okay. So example is, actually it's quite long, but let me just write it for you. Okay, so the example, integrations of x squared plus 2x minus 1 and then over 2x cubed plus 3x squared minus 2x. Okay. So first, if you can see the qx, if this can be factorized, then we can factor first. Okay. And I show you that this is factorable. And we can write this as okay, if I remove the x, let me write here first. So I have 2x squared plus 3x minus 2. We can factorize this. This becomes 2x minus 1, and then x plus 2. Okay, dx. Now, we can separate, okay, based on this multiplication in the bottom. We can separate, become three functions, okay? So this become, let me write this. The first one is x. Just plus them. Okay, we still don't know if it is plus or minus. Okay. And then 2x minus 1. And then plus x plus 2. Okay. Or maybe we are not using the integral first. So we just consider only the functions first. And then at the end, maybe we can add the integration notes. Okay. And to find the constant, I just write this a, b, c. Okay. And we need to find the a, b, c from this equation. Okay. How to find it? You see this whole functions in the bottom, divide by x and multiply by a, and write that. The same thing with b and c, and you need to equal them with the top one. Okay. It's like you did the reverse from here. Okay. So let me write for you. So a is 2x minus 1, x plus 2, right? And then plus b, it's x, and then let me write just x and x plus 2, and c is x and then 2x minus 1. Okay. And this should be equal to x squared plus 2x minus 1. And we can solve this, okay, and find the ABC. Okay. So let me write in a here. So 2a x squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus 2cx. Okay. Let me keep now grouping all the variables. So x squared is 2a plus b plus 2c. And then plus x is 3a plus 2b minus 2c. Oh, wait. It's wrong. It's x. And then we have minus 2a. Only minus 2a. So x squared, x, and the constant. Based on our findings, the only constant is 2a, right? So 2a is same as this constant. So a is half. So a is half. and then 2a, b, 2c is 1, and 3a plus 2b minus c is 2. We solve this, okay? We get b is 1 over 5, and later c is 1 over 10. Okay. So we can finish this ABC. It's become half 1 over x, okay, plus 1 over 5, 2x minus 1, plus 1 over 10, 1 x plus 2. And if you want to evaluate the integration, you can integrate and add the x, integrate and add the x. Okay. Yeah, it's quite long, and you need some works to do. Okay. My suggestion is you try doing these parts by yourself. Okay. Finding A, B, C. Okay. So the conclusion here is if you can find the bottom part of the rational functions, you can find it, you can factorize it, and you can make it into separate functions. You can do this whole process. Okay. You can find the constant first. Okay. But meanwhile, if you are maybe getting the bottom part here, maybe one of them, you cannot factorize. The determinant is less than 0, right? If you cannot factorize, or you cannot reduce the factor, then maybe you have like x squared something constant. Then the top one should be in bx plus constant. Okay? If that happens. Okay? But if not, if all is linear factors, then the top is a constant, okay, A, B, C. Okay. Okay, I think I will just stop here, and I will deliver you the results. Okay, someone from the international students, can someone come to the front, helping to separate your traffic? Can you help me? Maybe one from the global and maybe the College of Engineering. You can check.
No, we separate. Kumar too.
Okay, you can separate and look if there is. I think this.
Ini kasih mereka ya begini.
Yeah. Saya bawa kok. Nanti aja habis buka.
Kalian sih mau ke
Oh. Wait, still some still here. Hmm? Apa? Ini kayaknya dua lapis. Nanti juga ketemu. Can you look from here? Yeah, you can check from here. Oh, okay, okay. I think this is yours, right? Oh,
Ini per waktu, Sir. Aduh, sangat
ngaco.
Sir, kalau bisa
Tapi
kerja
maksimum
sekarang,
8, cuma 8 kok maksimum.
bisa tambah 2 nggak, Sir? Kalau bisa kerja
Enggak
sekarang.
ada tambah-tambahan lagi. Okay, I want to know who is B10931026. Okay, and 35026 is you, right? Okay. Uh, both students get 100, so I'll give you a present. Okay. Congrats, congrats. Okay.